Flack math! Give me some math and I'll give you some flack. Flack math!
So, today we're going to solve and graph inequalities. Do you guys know what an inequality is? Did we talk about this? What's an inequality? What's an example of an inequality? What does inequality mean? Not equal, that's right. So if it's not equal, then what is it? So if you have two numbers and they're not equal, then what could they be? Yeah.
Greater or smaller.
Okay, so that's basically what an inequality is. There's the obvious inequality of not equal to, but then you've got less than, and then you have greater than. And technically, these guys are still considered inequalities, even though that means less than or equal to, greater than or equal to, but they're still considered inequality symbols. Okay, so solving inequality, or equations, is basically the same word as an equality. So if I have something like this, x plus 2 equals 5, that means my balance scale is 5 over here, x plus 2 over here equal to x is equal to 5. So there is balanced, right? That's an equation or an equality. So if I had x plus 2 is greater than 5, then this is what the balance scale would look like, right? X plus 2 is greater than 5. So your goal in an inequality is not to change the scale, not to try to balance it out, but to keep it the same, just like we do with equations. So how do you get this x by itself? How do you solve this equation? What do you do? Kiara?
You subtract 2 from both sides.
Right. Or you could just think about it long enough and you know that it's 3, right? So what you're doing in an equality is you're taking the same weight off of this side as you are this side, so it doesn't change the balance scale. So x equals 3. Now what happens if you do that same thing over here? So right now it looks like this, right? Because x plus 2 is greater than 5. So when you take 2 off of this side and 2 off of this side, what is this scale going to look like? What's going to happen when you take the same weight off of both sides? Stay the same. That's the goal. You still want it to be the left side to be greater than the right side. So here's what ends up happening. We have a simpler way to say a certain amount of weight plus 2 pounds is greater than 5 pounds. Well, there's an easier way to say that. You can just say a certain amount of weight is greater than 3 pounds. Okay? So if I were to graph this, then this is what it looks like. On a number line, you guys know, I don't think you've ever done this. There hasn't really been a reason to. But how would you graph x equals 2 on this number line? You've done it on a coordinate plane, where you have 2 number lines, right? A horizontal and vertical axis. But how would you graph x equals, 3 on this number line? What would you do? What do you think? Ian?
Would you just mark the 3?
Yeah, just like I did on my shirt right now with this black marker. So you just put a dot on 3. You just mark 3, okay? That's what we do on a coordinate plane, right? When we have like 2, 3, we go over 2, up 3, and we put a dot. That's what it means to equal 3. X equals 3. This is the graph of x equals 3. What about x is greater than 3? What would that look like? And you guys probably did this in pre-algebra. What would the graph of x is greater than 3 look like? Well, what numbers are greater than 3?
4 dot dot dot.
4,
5, 6, 7, 8.
yeah. What, and just to infinity, that's it? What else is greater than 3?
The decimal.
Yeah,
0.5.
everything in between except not 3 and anything below 3. So how do you graph everything but 3? You do an arrow, okay? And so my eyes are 52 years old. So basically I can get really close. You can probably get closer because you have less than 52-year-old eyes. But I can't, how do you get as close as you can without touching? Because no matter how close you get, you guys remember this? Do you think I can get closer with my fingers? I can get infinitely closer with my fingers, right? And theoretically, I can cut the distance in half, cut the distance in half, cut the distance in half forever, theoretically. What does it mean if it's not theoretically, but practically, right? Practically, that's impossible because you can't just keep cutting it in half forever. But theoretically, you can cut a distance in half forever, right? What's half of an inch? Half inch. What's half of a half an inch? Quarter inch. What's half of a quarter inch? An eighth inch. So theoretically, you can keep getting closer and closer. So we're in trouble. So you have to shade everything but 3 and below 3. So we mathematicians, I wasn't a part of this decision, but we had to create a symbol. This symbol is called the everything but, okay? So here's what helps me remember the everything but. You're wanting to protect the 3. You don't want the 3 to get shaded, so you have to create a force field around 3. Did anyone ever watch like cartoons of the Super Friends? You probably did. Remember Wonder Woman's jet?
No.
The invisible jet.
Did you?
I feel like I didn't watch that.
Were you like a Marvel kid person or a DC kid person? Because
I was like Sesame Street.
and okay, I guess.
Sorry.
So Sesame Street didn't have any jets, but Wonder Woman's jet. Wonder Woman was my favorite. Don't judge, but she was awesome, and she had a jet, and it's an invisible jet. Okay, but it wasn't really invisible because we saw it, right? We just saw the outline of it. So the cartoon artists, it's like they forgot to color it in or something. So that's what the jet looked like, but it was technically invisible, but we as viewers were able to see it. So she was just sitting like this through the sky and just riding around in the sky. Okay, so we have to create a force field around 3 to protect it. So that's an everything but. The other thing you can think of is, see, obviously there's space there. There's like 3.0001 is not shaded, Mr. Flack. What's the deal? But this is just a symbol. This is not a practical graph. This is a theoretical graph of this, where this is, it communicates everything but 3, but don't shade 3, okay? So this is 3.0000000001, and you can get as close, even infinitely closer than that, and all the way up. But that's what that symbol means. Okay, and remember when we want it to be x is equal to 3, we fill in the dot. But when we don't want it to be 3, we don't fill it in. So technically you could do this. This is still the graph of x equals 3. Because open circles mean don't include those things. This means don't include those. So this is technically still an okay answer. I did way more work than I had to, but this is still x equals 3. Okay, so open circle means a force field protecting that from getting shaded. Okay, good? All right, so what do you think this graph is going to look like? So let's do that same equation with a different symbol. Let's try x plus 2, this symbol. What does this symbol mean again? Can you see it? What does this symbol mean?
X plus 2 is less than or equal to. and
Less than or equal to. Okay. So what does it mean to be less than 3 again? How do I shade that? If it was just less than 3, how would I shade it? How would I shade X is less than 3? How would I shade that? Yeah, Kiara?
You would circle the line that's
The 3?
the 3,
Yep.
and then you would shade everything under it. Which would
Okay,
go to negative.
now, what does it mean to be equal to 3? You fill it in, you shade it in. So this is less than or equal to 3. So when there's a filled in dot, that means 2 things. That means, well, filled in dot with shaded to the left or right, that means it's equal to 3 because it's filled in. That's what filled in means. Some other student gave the example of battleship, right? Like the misses are, I guess the misses they're like whites and reds, but like when you hit it, if you hit someone's battleship, then you put the peg in the hole, so you fill it in when you hit it. When you don't want to hit it, you keep it empty. Okay, so filled in means equal to, and it means the shaded to the left means less than. Okay, so this is something that students forget all the time, but you're not going to do it because you're different students. You're special. You're special people. Okay, so let's try another couple things here. What if I just said, what if I said this? Let's go. Well, okay, let's not do that. Let's do one more and then we'll call it good. So you have to be able to go backwards too. Let's write an inequality. An inequality, remember, looks like this. Has a less than or equal to sign, or greater than or equal to, or less than or greater than, of this graph. So I'm going to give you a graph, and you need to be able to tell me what the graph is of this, or what the inequality is of this. Okay, can you do that? Here we go. Ready? Ready? Oops, I did 2 -3s. That's embarrassing. Okay. Think about it. Don't answer it right away. Think about it and tell me what the inequality is going to be. So here's where you could start. You could just skip the inequality because the easy part here is the x, right? We can write an x, and we can write what number it's either less than, greater than, or equal to, or whatever. So you can start here. And then do you remember back in Math 7 when there's these big circles and you had to like put whether it's less than or equal to, or you remember that? And then did you guys do the whole crocodile thing, alligator thing? Crocodile eats the bigger number. But see how this isn't going to work now. It's not going to work with algebra. So you have to let them go. Did you name your alligator or crocodile? The shark? He was your friend. He got you through some rough times. It's time to let him go. Okay? Elliot, I know it's sad. Let him go. Let him go. Okay, so what do you got? What's your symbol? Okay, greater than, is it greater than or equal to, or just greater than?
Just greater.
Yep, just greater than. So there's no equal to symbol underneath there. Here's another way to think about this. If it takes less ink or lead to create that graph, it's going to take less ink or lead to create the symbol. Okay? So if I, over here, remember this took more ink or lead to create that symbol, so it's going to take more ink or lead to create that graph. Okay? Does that make sense? Can you guys remember the difference between those two? Have I exhausted this so much that you're like, we know this, Mr. Flack, move on? Is that what you're thinking, Addie? Okay. All right. So that's 37. Let's do 38 real quick. And then I want to give you guys some times. Oh, we're gonna do the fish method. This fish method is famous. It's in multiple films. It was in Where the Boys At? Sleepy Stew. That's the only thing he got out of school was the fish method.
That's all I got out of school.
Yeah, I guess so. That's why you're here, because you're trying to learn more math.
I'm trying to remember this stuff. I was
Okay.
holding on to the alligator.
It's all right. You can have a little memorial service if you want. I'd be willing to host it in my room. I did that with Ava's fish. Do you remember that? Were you part of
Didn't you
that?
play a video of fish frying?
That was a little insensitive. But apparently when Ava was in 8th grade or 9th grade and Janae, they had fish that died, which, you know, was sad, but they wanted to do a little memorial service and they wanted to know if they could use my room. So they did, but then I had a YouTube video playing of like, you know, like the fish sticks broiling in the broiler. It was probably insensitive.
It was. But,
Yeah.
You know, a couple years now, it'll be
Yeah.
funny again.
She's okay. We've talked. We've spoken since. Okay, we are going to talk about rate problems. What's a rate again? What's an example of a rate? What's a rate?
At what speed you're going.
Yeah, like that's like a miles per hour type of thing. Okay, or and rate comes from the same word basically as a ratio. So this is actually these are ratio problems. So we're gonna do a little scenario. Do you guys know how to calculate a ratio? What's the ratio of boys to girls in this class?
2 to 4. Oh wait, no.
I was like, yeah. So you're not including Audrey or Mrs. Knadison.
We don't count anymore.
2, 3,
Yeah.
4, yeah.
I see. I thought the fish sticks were insensitive, but you know, yeah, that's pretty hurtful. So yeah, let's just count everybody because that's better. So we're gonna go 3 to what is that? 6? Oh wait, that's still half. That's fine. Okay, let's not count me. Let's not count the adults. I did say boys to girls instead of, you know. Anyway, you guys are little. I'm gonna stop. Okay. So, boys to girls. So 2 to 5. Okay. Boys to girls, and you have to do it respectively. So if I go ratio of boys to girls is 2 to 5, or you could write it like this, 2:5, or you can write it like this, 2 to 5. I didn't even plan that, but that's cool. That's a little triangle. Okay, so 2 to 5, and so this one has to be boys, this one has to be girls. Now, if we would have included everybody, then that would have been 3 to 6. But just like a fraction, you can reduce that, right? If it's 3 to 6, that's just a 1 to 2 ratio. So this does not mean that there's 2 boys and 5 girls. It does in this situation. But if I said the ratio of boys to girls is the same in this class as it is in the whole school, then that would mean that the number of boys and number of girls would be equivalent to 2 to 5. Okay, now, here's a question that a lot of students don't get. What fraction of the class are boys? Let's go with this ratio. What fraction of the class are boys? Do you know?
I'm scared to answer.
You should be. What fraction of the class are boys? if it's a 2 to 5 ratio, what fraction are boys? Do you know?
2/7.
Nice! Crushed it. So,
Should have answered.
so what fraction are boys? What fraction? See how fraction, a lot of people think, oh, ratio's just a different type of fraction. When I think of fraction, I think part of a whole, right? So what fraction are boys? It would be 2 out of 7, right? 2 out of 7. So how do you say out of? That translates to the little fraction bar. This is not 2 out of 5. This is not 2 out of 5, right? This is 2 to 5, or 2 for every 5, but it's not 2 out of 5. So don't think of a ratio as a fraction, because when you think of a fraction, that's like a part of a whole, right? Where this is the part and this is the whole. So 2 out of a total of 7. Okay, so we're going to just do some word problems, and we're going to try to find the missing numbers. So if it's a 2 to 5 ratio, then one example could be maybe there's 20 boys and 50 girls in the school right now. Okay? 20 boys and 50 girls. That would be equivalent to 2 to 5. Because even though we don't like to think of this as a fraction, it is a fraction, but equivalent ratios are like equivalent fractions. Okay? So let's try this. Let's try, let's say, ratio of pigs to goats. So I probably shouldn't have said that right after I talked about the boys and girls, and I just called them pigs and goats. No, now we're out of the school, we're on a farm, okay? Ratio of pigs to goats is 7 to 5, okay? Ratio of pigs to goats is 7 to 5. So far, so good? Are you visualizing this farm? Can you smell it? I smell it. I had one of my dad's friends was a pig farmer, and we used to go up to his farm and ride tractors and stuff. We used to live in Iowa, okay? But it was a pig farm. Obviously, it smelled terrible, but it's kind of one of those smells that you like. Like when I drive through Greeley, it smells like cow poo, but it's kind of like one of those scents that you're like, no? It's like, because it's sentimental to me. It reminds me of home. It reminds me of home. Ratio of pigs to goats, 7 to 5. So let's say there's 91 pigs. My marker's doing bad things. 91 pigs. So how do you figure out how many goats there are if you know that the ratio is 7 to 5, but there's 91 pigs? How many goats? How do you figure that out? Do you know?
Turn it into a decimal and then multiply it.
That's a good option. So you could do like
turn 7 to 5 into 1.4 and 91 times 1.4.
Yeah, 1.4. Okay. You could do that, but you're going backwards, because it wouldn't be times, it would probably be divided by. That's one way to do it. Yep.
65.
65. Okay, how'd you get that?
I divided the number of pigs by 7. And
Okay.
multiplied it by
Okay, so let's try to visualize what he did. So let's write the ratio as a fraction. 7 to 5 equals, well, pigs go first, right? Pigs are on top. So 91 goes here. And we're just trying to find the missing number in this proportion. Thus, the fish method, but we'll get to there. So what Elliot did is, just like we multiplied this by 10 to get 20 and 50, you can multiply this by something. What was it, 13? 7 times 13. So he divided 91 by 7. And he probably didn't write this out first. He just did this in his head. But I would write it out so you can see what you're doing. Because that's the rule for equivalent fractions, right? It's like the golden rule. Whatever you do to the bottom, do to the top. Or whatever you do to the top, do to the bottom. Well, you have to multiply 7 by 13 to get 91, so multiply 5 by 13 to get 65. Okay, that's one way. The other way was, this is a 1.4 difference. So 5 times 1.4 equals 7. So what times 1.4 equals 91? Well, 91 divided by 1.4 equals 65. I promise, it does. Okay? That seems a little complicated to me, but if that works for Ian, Ian's gonna do that. Here's my favorite way. You've got that vertical relationship that Ian just said. There's a relationship between 5 and 7. It's that same relationship between 65 and 91. You also have this horizontal relationship of 7 and 91. 7 times 13 is 91, so 5 times 13 is 65. Now you have a diagonal relationship. Watch this. 91 times 5 equals 455. Guess what 7 times 65 equals? I'll give you a hint. 455. So cross products in an equivalent fraction or a proportion are always the same. So guess what you get to do? You get to multiply, because this has to equal 455 too, right? So here you have to go 91 times 5 to get 455. And then you ask yourself, what times 7 equals 455? In other words, 455 divided by 7 equals 65. What did I just draw? See that? That is the fish method. Okay, now you can draw the fish however you want. Like you can draw this fish, which is a chubby swimming upstream fish. Okay, that's a nice fish. So it doesn't matter how you get there. You got to figure out what the cross products are supposed to equal. Well, you will only ever have one cross product that you can calculate, because you don't know what this number is, so you can't calculate that cross product. But you can calculate that. 91 times 5 is 455 divided by 7 equals 65. Luckily, you can use your calculator and you can do that all in one thing. 91 times 5 divided by 7. Okay? All right, let's try another one and then we'll be done. Chickens to ducks. This is I'm not saying ducks because of that, but this is just in the book. So
Thank you so
Yep.
much. That was
Right.
really fun.
she's gonna go report to Russia everything that
So,
she
like,
heard.
All
So
the secrets from this
Yeah.
classroom.
that's right. See ya. All right, chickens to ducks. Chickens to ducks. Chickens to ducks is 9 to 4. Okay. And then there's 108 chickens. 108 chickens. How many ducks? So it's going to give you the ratio. It's going to give you one of the actual numbers. And then it's going to ask you to find the other one for now. So here's my quick hack, math hack. Ready? Flack math hack. Flack. Here's my math flack. Here's my flack. Here's my hack attack. Flack.
Your Flack hack.
Flack hack. Flack. Ava's just like, this is Ava. This is what she's like. Well, I'm doing all this. I think she thinks I'm having a stroke. Okay, here's my flack hack. That's good. When you don't know, tic-tac-toe, baby. Right there. Baby. Chickens, ducks. And then you've got a total, which we're not going to use today, but we will later. This is your ratio column, and this is your actual number column. Okay? 9 to 4. Chickens go there. 108. Look. You've got your proportion already there. Boom. You see that? So now you can just fish it on home. You could do, this is actually times 12, so 4 times 12 is 48. Or 108 times 4 is 432 divided by 9 is 48. Right? Did I get that right?
That's
Yeah.
what I got.
Okay, good. So 48 ducks. There's now 27 ducks over there. So somewhere in this building there are almost 108 chickens, if there's 27 ducks. Let's calculate that ratio, okay? So if this is the same ratio of ducks, chickens and ducks in this school, I've got 9-4, right? Well, I've got 27 ducks, right? So how many chickens is that? It might be a piece of chicken. Something and a piece of chicken. What do you got? Because 4, we can't do it the nice equivalent fraction method because 4 doesn't go into 27. Unless I got another duck. Did I get another duck? Nope, still 27. So, how many chickens is this? This is equals, by the way. Yeah, what is it?
60.75?
60.75. So, it's 3/4 of a chicken. So, there's a chicken out there with 3 legs running around. Well, maybe they're not live chickens. Maybe they're little plastic chickens like this. Either way, it's not a full chicken. So 60 chickens and then part of a chicken. All right, are we good? Can you guys do these ratio problems? This is nice. You've got a little tic-tac-toe thing. We're gonna utilize this 3rd row eventually, but for now you can just use those top 2 rows of a tic-tac-toe thing and just write your ratio, write your actual numbers, and this kind of keeps you, it organizes your data. And organizing data in math is half the battle, okay? If you're not organized in math, it's not gonna be very enjoyable. All right,